Okay, so good morning everyone. So I am your physics teacher and you can call me Teacher Myra. So today we will be going to discuss what is a solid state physics. So what is a solid state physics? So it is a branch of physics which deals with the practical and theoretical investigations of the properties of solids such as superconductivity, photoconductivity, and ferromagnetism. So in other words, it is the study of solids through various methods like crystallography, quantum physics, electromagnetism, and metallurgy. So solid-state physics is the most important branch of condensed matter physics. It helps to investigate how the large-scale properties of solid materials result from their atomic scale properties. Thus, physics forms a theoretical basis of material science. So, what is a solid state? So solid state can be single crystals. It is a long-range order and 3D translational periodicity. An example for this is a graphite. And next we have the polycrystalline crystals. So it is a single crystals assembly, and an example for this is a diamond. And third one is the amorphous materials. So it is a disordered or random atomic structure. An example for this is a silicon. So there are classification of solid materials. So these are crystalline, polycrystalline, and the amorphous or non-crystalline. So when we say crystalline solids, so crystalline materials are solids with an atomic structure based on a regular repeated pattern. So crystalline materials are characterized by a highly ordered atomic structure where atoms are arranged in a repeating pattern that extends throughout the material. So this regular arrangement gives rise to the unique properties of crystalline solids, such as their well-defined geometric shapes, distinct cleavage planes, and predictable physical properties. So the atomic arrangement in crystalline materials follows specific crystal lattice structures, leading to the formation of crystals with defined shapes and symmetries. The second one is the majority of all solids are crystalline. So, in the realm of solid materials, the majority exhibit a crystalline structure. So this prevalence is due to the natural tendency of atoms and molecules to arrange themselves in an ordered manner, forming crystals. So crystalline solids are abundant in nature and encompass a wide range of substances, including metals, minerals, and many synthetic materials. So the regular atomic arrangement in crystalline solids contributes to their stability, durability, and characteristic properties, making them essential in various industries and applications. And the third one is more progress has been made in understanding the behavior of crystalline solids than that of non-crystalline materials, since crystalline materials are more stable. So scientists and researchers have made significant advancement in comprehending the properties and behavior of crystalline solids compared to non-crystalline or amorphous materials. The ordered atomic structure of crystalline materials provides a well-defined framework for studying their mechanical, thermal, and optical characteristics. So the stability inherent in crystalline structures allows for more accurate predictions of material behavior and properties, facilitating progress in material science, engineering, and technology development. And, in, and examples for this includes most metals, ceramics, calcite, and etc. So crystalline materials encompasses a broad spectrum of substances with examples ranging from metals to ceramics and beyond. So metals such as iron, copper, and aluminum typically exhibit crystalline structures due to the ordered arrangement of metal atoms in a lattice. So ceramics, which are compounds of metallic and non-metallic elements, also commonly display crystalline properties. So these materials demonstrate the diverse applications and importance of crystalline solids in various fields including manufacturing, construction, electronics, and more. Okay, so now we are done with the crystalline solids. So now let's proceed to the polycrystalline solids. So polycrystalline solids are materials made up of an aggregate of many small single crystals, also called as crystallites or grains. So polycrystalline materials consist of a collection of numerous small individual crystals known as crystallites or grains. So each grain within a polycrystalline structure exhibits a regular and ordered atomic arrangement characteristic of a crystalline solids. So the presence of multiple grains in a polycrystalline material results in a complex network of crystals orientations and boundaries, giving rise to unique mechanical, electrical, and thermal properties. So next is polycrystalline materials have a high degree of order over many atomic or molecular dimensions. So despite being composed of multiple individual grains, polycrystalline materials exhibit a high degree of order over numerous atomic or molecular dimensions. So each grain within the polycrystalline structure maintains a well-defined crystal lattice structure, contributing to the overall ordered nature of the material. So the regular atomic arrangement in each grain imparts specific properties to the polycrystalline material as a whole, making it suitable for a wide range of applications. Next is the grains or domains are separated by grain boundaries. So the atomic order can vary from one domain to the next. So in polycrystalline materials, grains or crystalline domains are separated by interfaces known as grain boundaries. So these boundaries serve as regions where the atomic order may differ between adjacent grains, leading to variations in crystal orientation and properties. So the atomic structure across grain boundaries can exhibit defects or misalignments, influencing the material's mechanical strength, conductivity, and other characteristics. So grain boundaries play a crucial role in determining the overall behavior and performance of a polycrystalline materials. So on the next one is the grains are usually 100 nanometer to 100 microns in diameter. So the size of grains in polycrystalline materials typically ranges from 100 nanometers to 100 microns in diameter. So these grains vary in size depending on the specific materials and processing conditions. Okay, so on the next one is the grains are usually 100 nm to 100 microns in diameter. So polycrystalline materials with the grains smaller than 10 nanometers in diameter are classified as nanocrystalline. So nanocrystalline materials exhibit unique properties resulting from the ultrafine grain size, including enhanced strength, improved hardness, and increased thermal stability. So the nanoscale dimensions of grains in nanocrystalline polycrystals offer opportunities for advanced materials with novel properties for various technological advancements and applications. So next is we have the amorphous solids. So amorphous solids are solids made up of randomly oriented atoms, ions, or molecules that do not form defined patterns or lattice structures. So amorphous solids, unlike crystalline materials, amorphous solids lack a well-defined atomic arrangement and do not exhibit the regular repeating patterns characteristic of crystals. So in amorphous materials, atoms, ions, or molecules are randomly oriented and do not form specific lattice structures. So this randomness in atomic arrangement results in the absence of long-range order, leading to unique properties such as isotropic behavior and lack of cleavage planes. Next one is the amorphous materials have order only within a few atomic or molecular dimensions. So while amorphous materials lack long-range order, they do possess some degree of order within a limited range of atomic or molecular dimensions. So this means that the atomic or molecular arrangement in amorphous solids may exhibit short-range order, while local clusters or groups of atoms have some degree of alignment or coordination. However, this short-range order does not extend throughout the material, distinguishing amorphous materials from crystalline solids. And the third one is the amorphous solids do not have any long-range order, but they have varying degrees of short-range order. So the lack of long-range order in amorphous materials is a defining characteristic that sets them apart from crystalline solids. So while amorphous materials exhibit randomness in their atomic arrangement on a larger scale, they can display varying degrees of short-range order at the local level. So this short-range order may result from local structural constraints or interactions between neighboring atoms, so leading to the formation of clusters or regions with some degree of alignment. So the presence of short-range order contributes to the unique properties and behaviors of amorphous materials. So an example for this includes amorphous silicon, plastics, and glasses. So, um, glass, for instance, is a well-known amorphous solid that lacks a crystalline structure and exhibits random atomic arrangement. So amorphous polymers, such as some types of rubber or plastic materials, also demonstrate the characteristics of amorphous solids with short-range order but no long-range crystalline structure. So gels, which are colloidal systems with solid-like and liquid-like properties, can exhibit amorphous behavior due to the random arrangement of their constituent particles. Okay, so why most solids are crystalline in nature? So first, nature always loves the symmetry. So symmetry is a fundamental principle in nature where objects and systems exhibit balanced and harmonious arrangement. So symmetry plays a crucial role in the structure and behavior of natural phenomena from the atomic level to the cosmic scale. So nature tends to favor symmetrical patterns and arrangements due to their aesthetic appeal and efficiency in organizing matter and energy. Second is symmetry measures the stability. So in physics and chemistry, symmetry is closely linked to stability. So systems with higher degrees of symmetry are often more stable and less prone to disruptions or deviations from equilibrium. So symmetry provides a measure of the balance and order within a system, reflecting its stability under various conditions and interactions. And the third one is stability indicates the state with less energy. So stability in physical systems corresponds to a state of lower energy. Systems naturally tend to adopt configurations that minimize their energy content to achieve a stable equilibrium. So lower energy states are associated with greater stability as they represent energetically favorable arrangements that require minimal energy input to maintain. And the fourth one is crystalline solids exhibits with less energy. So crystalline solids characterized by their ordered atomic structures and regular repeating patterns represent configurations with lower energy compared to disordered or amorphous materials. So the well-defined lattice structures in crystalline solids results in more stable arrangements of atoms, requiring less energy to maintain their integrity. The atomic order in crystalline solids leads to lower energy states, contributing to their stability and durability. And fifth one is, therefore, crystalline solids are more stable. So based on the principles of symmetry, stability, and energy minimization, crystalline solids are indeed more stable compared to non-crystalline or amorphous materials. So the ordered atomic structures and symmetrical arrangements in crystalline solids result in lower energy states and greater stability, making them preferred materials in various applications where durability, predictability, and reliability are essential. So the inherent stability of crystalline solids, due to their organized atomic arrangements, aligns with the broader principles of symmetry and energy minimization in nature. Okay, so now we have the differences of the crystalline and the amorphous solids. So a crystalline solids, it has a regular three-dimensional arrangement of atoms, ions, or molecules due to which they have well-defined geometrical shape. While the amorphous solids, it do not have regular arrangement of particles, therefore do not have well-defined geometrical shape. And the crystalline solids, they have long range order, and the amorphous solids, they have short range order. And the crystalline solids, they have sharp melting point, while the amorphous solids, they do not have a sharp melting point. And the crystalline solids, they are anisotropic, and amorphous solid, they are isotropic. So, and that is all for today's discussion class, and goodbye. So we'll continue this discussion next meeting.